So I thought I would take a little bit of a breather with a different kind of example here. Now I'm going to characterize this graph-theoretic claim in terms of having a party, okay? So I'm going to call this party time. Party time, excellent. So suppose you are hosting a party with n greater or equal to 2 people. We're going to have 2 or more. That includes yourself as well. There's 2 or more people at this party. Now, people at a party may be friends or they may not be friends. But the point I'm getting at is that, and this is going to be actually an important nuanced point here, is that we are going to define that friends are mutual. So people are either mutual friends or they're not. So for example, if Miss Kitty's having a rough day and she doesn't want to be friends with me, that doesn't count as being my friend because it's not reciprocal. It's not mutual. Okay? Now keep in mind that Miss Kitty's still my friend, but I'm trying to be a bit playful with this, okay? So people at the party so when I say be friends, I'm talking mutual friends. Mutual friends or not. Now, this is where it's going to get a little bit weird, especially if you've never seen this before. Here's my claim. Here's the claim. Some pair of people at the party are friends with the same number of people at the party. So let me just say this again. Some pair of people at the party are friends with the same number of people at the party. So that means that there's going to be 2 people that if you asked everybody at the party who's friends with who, and you tally up how many friends they have, there's going to be 2 people that are going to give you the exact same count. That's what the statement says. It doesn't say that they're the same set of friends, just to be very clear. It's just that the number of friends between these 2 people are the same. So I want to give you an example of how we could prove this claim in a couple different ways. So this is mainly to illustrate for you that you could use the pigeonhole principle in a couple different ways. We've seen an example where we directly use the pigeonhole principle. So I'm going to start off first by proving it directly, this claim, and then I'm going to prove it using contradiction, just to show you. And I'm hoping the first time you go through, you'll get some ideas of how we would go about proving this. Then the contradiction proof will go a lot smoother. Smooth like a banana peel on a wax floor. So we're going to actually present 2 proofs here. So proof 1 is going to be based on a direct argument. So here's where we're going to start. We're going to examine the numbers of friends. The numbers of friends a person can have at the party. Seems like a pretty sensible place to start, as we just find out how many friends can a person have at the party, right? So let's just see what that's about. the number of friends a person has at the party is at least what? Can somebody be at the party and not be friends with anybody? Technically, by our way characterizing being at a party, yeah, somebody could be at a party with no friends there. There could be somebody with no friends at all at that party. Maybe they just got an invite from somebody and they just showed up, but they weren't friends with anybody. Just some random schmo that showed up. At least 0. And at most what? Now, notice that I said mutual friends. You can't be mutual friends with yourself, okay? You're friends with you could be mutual friends with somebody else. So there, you could have at most n minus 1 friends if there's n people at the party, right? So it's something between these two. Now, depending on this fact, so now we know that every person can have at least 0 friends and at most n minus 1 friends. We're going to break this into 2 possible cases depending on how our party is configured. So, for example, is there a friend that has 0 friends? Sorry, is there a person at the party with 0 friends? That may or may change how we might go about this. So let's watch what happens. So there are 2 possibilities. So we're going to break it into cases. So it's technically a proof via cases. There are 2 possibilities. So using the information we just absorbed here, absorbing it like energy from the sun, like Sunny D or something. Just suck it in my veins. So there's 2 possibilities. So as I've already told you, there is a possibility that somebody at the party has 0 friends. So case 1, a person has 0 friends. If they have 0 friends, I have a question for you. If there's n people at the party and somebody has no friends, can there be somebody with n minus 1 friends? Like say Miss Kitty. Miss Kitty shows up at the party, nobody's friends with Miss Kitty because Miss Kitty's being a bit of a something. Maybe everybody was just a little upset with Miss Kitty that day. But still they're their friend, but you get my point. Is that suppose that just for the fun of it that nobody's friends with Miss Kitty that day. She's coming in trashing your boxes. But if that's the case, can anybody have n minus 1 friends? No, nobody can. Nobody can in that case. Because you would have to be friends with Miss Kitty. You would have to be if you have n minus 1 friends. But that person has no friends at all. Then, no person can have n minus 1 friends. Can have n minus 1 friends at the party. So what does that mean for the number of possible friends that somebody can have then is? Well, we've definitely constricted it. It can't be, in this case it can be 0, but it can't be n minus 1, right? So the possible number of them, it may be some subset of this in reality, but most certainly it cannot be, what does it mean? The numbers of possible friends a person has is 0, 1, 2, all the way up to n minus Is it n minus 1 or is it n minus 2? It's n minus 2. You can't have it be n minus 1. So just to reiterate, a person has 0 friends. In that case, no person could have n minus 1 friends at the party. The numbers of possible friends a person has is 0, 1, 2, all the way up to n minus 2, but not n minus 1. Not n minus 1 at all. You can't have n minus 1 friends in that scenario. Otherwise, every person has at least 1 friend. Right? That's the only other possibility out of these two. You can exhaust this to more cases, but this is everything else but that. Every person has at least 1 friend. So in this case, then the number of the numbers of friends that people can have, it doesn't include 0, right? That just seems rather straightforward, right? The numbers of possible friends a person has at the party belongs to, give me a drum roll. It's gonna be in this set. 1, 2, 3, all the way up to n minus 1. Well, what can you observe about both cases? How many elements are in both of these sets? N minus 1 many elements. How many people are at the party? N. So let's use that fact. Regardless, the numbers of possible friends a person has at the party time, at the party is less than the number of people at the party. Now, this is where we pull out our friend, the pigeonhole principle. Here we go. Therefore, by the pigeonhole principle, some pair of people are friends with the same number of people at the party. That completes the proof. So if ever you're at a party and you're looking for something to brag at somebody, pull out my friend Dre would be lovely for this. Get himself a notebook, start making a tally of how many friends are at the party. And my friend Dre could come up to you and tell you, hey, look, there's going to be 2 people that are going to have the same number of friends at the party. I didn't have to write it down, but I could tell you who they are. So that's what we could say for the pigeonhole principle in this case. So that's the direct proof. There's the key things I really want you to observe is how we use the fact that we could actually restrict the number of possible friends somebody can have at the party. In this case, we exhausted those possibilities. In this next version of this proof, we're going to be able to do a little bit less work, but it'll be enough to prove the claim. So let me just back up over here and we're going to see the second proof. So let me show you a different proof. This one's going to use contradiction. So for those that are just like, oh Dan, let's get to the graph theory, feel free to, if you're watching this in the future, feel free to pass what we're doing, but right now we're doing this all together. But I think there's something to appreciate about the contradiction version of this proof. So let me show you how we could go about this using much of the same ideas we did before. So here's the game plan. I'm going to assume otherwise. So that means that, what does that mean about this statement then? If it says there's some pair for which they have equal numbers of friends at the party, that means that no friend has equal numbers of friends at the party. Sorry, no person at the party has equal numbers of friends. So we're going to use that fact and it'll come out quite nicely. So that's the game plan. Assume otherwise. So assume otherwise, then no pair of people at the party have the same number of friends. But what does that mean? If they don't have equal numbers at all, that means that every single one of the people at the party, if I ask them how many friends they got, all of them are going to give me a unique number, right? That's what it means. This implies that every person at the party has a different number of friends at the party. So that means that all of them have a distinct number. But what did we say before? That we can actually characterize how many friends somebody can have at the party, right? We're going to do the same trick. Then the number of friends a person at the party can have is in this following set: 0, 1, 2, all the way up to n minus 1. For each value, now because remember there's n people at this party and there's n things here, right? So that means that each one of my friends at the party has to take on one of these numbers, right? I don't know who takes on what number, but there's only n of them there, right? Because 0 up to n minus 1, that's n of them, right? So that means I can't just simply say, oh, well, some of them might have the same one, because we already assumed that that isn't the case, right? For each value in this set, there is a person at the party, right? Now, we pull out our trusty trickery that we had last time. Now, it doesn't matter which version of this you would like to do, but the main thing I need to point at is that we could pull out our scenario where we had with Miss Kitty. So what did we say earlier about Miss Kitty? Miss Kitty's got no friends at the party. People are upset with Miss Kitty. She knocked their box over. But suppose that you're maybe a really great host and you're friends with everybody at the party. So let's flip this around just to be a little bit positive about the whole scenario. Since one person must have n-1 friends, right? Somebody has to, because that's one of the numbers in there. No person has 0 friends. Miss Kitty, you're out of here. Oh yeah. So, sorry, that wasn't Miss Kitty. That was just me kicking air. Sorry, I'm having a little bit of fun with this. So the number of friends a person has are, I'll say is in 1, 2, 3, all the way up to n-1. It's got to be in this set because we know one of them has n-1 friends, so somebody can't have 0 friends. It's not possible. Since there are n people and the numbers of friends a person can have at the party is n-1. Now this is where we get pulled at the pigeonhole principle. By the pigeonhole principle. By the pigeonhole principle. At least 2 people have the same number of friends. But what does that mean? It's a contradiction, right? Because we assume that no, so it has to be, because this is a contradictory statement because we assume that no pair of people have the same number of friends. But by the pigeonhole principle, we said that now we're also saying that there are at least 2 people that have the same number of friends, which is a contradiction. You can't have both those 2 things be true at the same time. It's impossible. That marks the end of the proof. So this is how you could use the pigeonhole principle in the context of a contradiction proof. So notice that it doesn't change the nature of how the theorem gets used. It's just that the setup for how you get the argument to work, you mostly want to get it propped up so that the pigeonhole principle often is the thing that gets you the contradiction. So just use it very carefully if you're planning to use it like this. You'll find that many of the ideas we had actually came out of the first attempt we had. But either way, it's just something to think about. Now, I promised you I was going to show you how this connects up with something from graph theory. So let's talk about that now. Here's an application for graph theory. So actually, everything I've talked about actually has an equivalency with the statement in graph theory. But let me just give you an idea of what I'm talking about. Suppose that there, for example, were 4 people at a party. I'm going to represent these as vertices in a graph. You can just think of them as dots that represent the people, if that makes it easier. So suppose there's 2, 3, 4. Now, suppose person 1 is Miss Kitty, and we established Miss Kitty's got no friends. How about person 2? Person 2 maybe is friends with person 4, and person 3 is maybe friends with person 4. So notice that actually the relationships that I describe in the party actually are characterized by an undirected graph like this, because the friendships are mutual. So we're characterizing mutual friendships when we talk about our friendships here. So notice that there exists what we call an edge, whose endpoints are friends that are represented by vertices, if they are mutual friends. If there is no edge, for example, from 3, 1, that means that friends 1 and 3 are not friends, mutual friends with each other. So notice that actually what we've been talking about is actually a graph-theoretic statement. So let me put this all into context here. So in short, we've been talking about undirected graphs. So vertices are the people at the party, and the edges, these are these lines that, or connections between the vertices. Edges represent mutual friendships. As we discussed previously. Now, let me put this into fun graph-theoretic terms, okay? So we have this concept, and I've talked about this before, called the degree of a vertex. So this is simply the number of edges. And here comes a word that I'm just going to parse quickly for you. Incident on a vertex V. So we'll write this as dag of V like this. So this is the degree of a vertex. So what does it mean for edges to be incident on a vertex? So all you're doing is you're looking at the sticks, these edges that connect, that go out from that vertex. So for example, vertex 4 has degree, so the degree of vertex 4 is 2. The degree of vertex 1 is 0. Notice there's no edges going out. You count the number of edges that go out. The degree of 2 is equal to 1, right? It just says one friend at the party. And the degree of 3 is 1, right? So believe it or not, if you actually think about what we've just been doing all this time, this is actually a statement about the degrees of vertices in a graph. So we have the we have the following equivalent theorem. So you can take the proofs that we've given previously, regardless which form you would like them, just change them into graph-theoretic terms. You have the exact same argument, though. Is this one. So given a simple, now simple just simply means that you obviously can't be friends with somebody more than once, and you can't be mutual friends with yourself, right? So given that, so in a graph, that just simply means you can't have what we call parallel or multi-edges, and you can't have self-loops. But I have no doubt that there's easy ways to get around some of these things in some sense. But we're just going to talk about this more fundamentally. So here's the equivalent theorem here. So given a simple undirected, this simply means that the edges, there's no assignment of a direction on the edges. It just means that you can go from 4 to 3 to 3 to 4. It doesn't matter. It just represents a connection between these two endpoints of an edge, 3 and 4. Given a simple undirected graph, with at least 2 vertices, there are at least 2 vertices with the same degree. So this is a statement about simple undirected graphs, or just some people just call them graphs. It says that if you have at least 2 vertices, think of it as 2 people in the party, at least 2. What you could say is that there's always going to be at least 2 vertices, those are those dots over there that we've numbered. They're going to have the same degree. The number of incident edges are going to be the same for at least 2 vertices. Try as you might, you won't be able to come up with a graph where all of the vertices have distinct degrees. So that's an interesting connection between having a party with your mutual friends, or some people, some of them are mutual friends, and graph theory. Pretty neat stuff, right? And the way we can prove this quite nicely is using the pigeonhole principle.